Hi everybody, welcome back to science class. We are now starting in on physics. We have finished chemistry from last quarter, and this whole quarter is going to be about physics, specifically Newton's three laws and energy. So these first three units that we're going to do are Newton's first, second, and third law, and then our fourth unit before we end the quarter is going to be all about energy. So we have a lot of things to talk about because physics is a huge topic. If you're not sure what physics is about, I think that the best way to describe what physics is it's a way to describe the universe using math. If math is something that has been a scary topic for you in your life and something that you haven't really called one of your strengths, you should know that this class is designed, or I'm hopefully designing it, in a way where we're going to focus more on the concepts than we are on the numbers, but math isn't always numbers. Math is more of a way of logically thinking about things, if you haven't thought about math that way. And that's what we're going to do in this class. So for this first unit, we're going to talk about Newton's first law, and we're actually going to do that this very first day of this unit and describe what that law is. And we're going to unpack it more as we go throughout the unit. Each one of these units is going to be about 2 weeks as we go through the quarter together. So that's what you can expect as we go forward. I picked a few pictures to kind of represent some of the things that we're going to be covering. So we're going to be doing some things with graphs and these things called vectors. That's what these little arrows are, and it's a way to describe or predict where things are going to move and how they're going to move. We're also going to do Newton's second law, which is all about forces. And then Newton's third law, which is all about actions and reactions. You've probably even heard of that law before, if I'm guessing. There's these things called Newton's cradles. We're going to take a look at those. Those show all three of Newton's laws, and they're a really good way to summarize. And then we're also going to talk a lot about real-world things. So I just picked one picture of a crash test dummy. When people test cars in collisions, physics is king. They are constantly using the laws of the universe, like Newton's three laws, to figure out how a person might survive a car crash. I'm also going to use a lot of space examples because space is a really great way to think about how things will move because you can take out the ideas of gravity a lot of times, which helps. But these are some of the things we're going to be looking at. So as a quick reminder, you're going to be needing your science notebook for this class, just like last quarter. If you need to get a new notebook or continue in the last one, either way, that's fine. But every single lesson, you're going to have notes on the left-hand side, and your practice page is on the right-hand side. And anytime you need to do something in your notebook, I will let you know on the slide with the little symbol in the top corner, and I'll also just say it. So you're going to need that for today as well, just like every other lesson. Your job today is to restate Newton's first law of motion and use it in everyday circumstances. So your closure today is going to be a really close approximation of what your assessment question is going to look like. So hopefully when you hit the assessment for this topic, you'll be like, oh, this feels really familiar. Basically what I'm going to do is I'm going to show you an example of something moving, and your job is to explain how Newton's first law had to do with that, like what Newton's first law has to say about predicting what should happen next, stuff like that. We'll do a bunch of examples you'll see. If you haven't already done the warm-up, I need you to pause this video and do that first. The warm-up isn't actually attached to this lesson, though. So hopefully you won't be confused. The warm-up is actually what got posted on Monday. If you haven't already seen it, on Monday I posted a survey that had a couple of things in it. There are actually two technical forms that you had to fill in. One was a form about asking you about some of your personal preferences, and then the other one is a math and science kind of pre-test. I always get the question, is this graded? What if I don't do very well? Well, if you don't do very well, it means you're in the right class because you haven't learned those things yet. And if you are not doing very well, it tells me what things that we need to cover, and it kind of guides me and helps me to understand what you need to learn and where you need to get some help. And that's really helpful for me, obviously. So make sure you go back and do the warm-up first. All right, if you are still watching, that means that you have finished the warm-up and you're ready to get into Newton's first law. And the way we're going to start this is by playing a game called Hand Judo. Here's what Hand Judo is. It's a game that I made up, but basically here's how it works. You need to find an opponent, maybe a sibling or a parent or somebody, and you're going to do this in just a minute. And here are the rules. Your feet need to be shoulders width apart, and then you're going to face your opponent and put your hands up like this, and your toes need to be about 6 inches from your opponent. For me, that's about like the length of my hand. That's about 6 inches, like that. So you're going to be really close. If it feels uncomfortable, you know you're in the right spot. So you're going to get really close, put your hands up like this, and then the goal is to push your opponent and make them move their feet first. In other words, whoever moves their feet first loses. The one thing you can't do is grab onto them, so you can't like grab them and throw them to the side. The only thing that you can do is touch their hands, and you can't grab their hands. So there are two main strategies that we'll go over in just a minute. Here's a video that I made of me abusing my children that you can watch. So the first thing that people do wrong is that their feet are too far away. You need to be uncomfortably close.
Like that?
Not too close.
Or like that?
Like that. Perfect. Okay. Feet real close, put your hands up. Now, go. You can't grab on.
Okay, it's just hard. I don't know what to do.
Go. Oh, you moved your feet. Try again.
Whoa.
Okay, Cohen, your turn. Okay, stand right there. Feet shoulder width apart. You ready? Push Daddy over. You can't grab on. Okay, start over. Your feet like this. You can't grab my hands, you can only push. Try to push Daddy over. Try again. Okay, so I want you to actually go and find someone in your household to play hand judo with. Think about what advantages the winner had while you play. So if you are the winner, I want you to think about like what was it that gave you that advantage? There are probably a lot of things that you can think up. We're going to apply it to all three of Newton's laws as we go. Today we're going to talk about just Newton's first law because all three of Newton's laws have something to do with this game and how you can win. But you need to go and get some experience playing first. So pause this video. Go find someone to play hand judo with. If no one is home with you, I want you to find somebody before the end of the day to play hand judo with. Go play now. All right, so hand judo is all about manipulating the laws of physics to your favor. And if you understand the laws of physics, you can make the right decisions to make it so that you have an advantage. Well, we're going to start off with Newton's first law, as I said. And so we need to understand what Newton's first law is before we can take advantage of it. We're going to start off with a reading. So in Google Classroom, there is a PDF that says Newton's first law reading and student worksheet. And I need you to open that up using Kami. And your job is to do a couple of things. One, you're going to just read the article. While you're reading, I need you to underline or highlight using Kami the most important phrase or sentence from each section. So there should be one thing highlighted or underlined from each section when I go and look at it. Then at the end, there are 4 questions that I need you to answer. It looks like this. So the reading part starts off the document. This first little sentence is not a section, so you don't need to highlight or underline from there. But there's a section called force and motion. I need you to pick the most important part for you that you want to underline or highlight. Then there's a section called inertia. It's not pronounced inertia, it's pronounced inertia. You're going to underline or highlight one part from there. And then there's the last section here where it says inertia and mass. And you're going to do the same highlight or underline. Then there's a little summary. You don't have to highlight, but you should read it. And at the end, there are the 4 questions. All you need to do is open this with Kami and make sure that you are typing in all of your answers into these 4 boxes, or 1, 2, 3, 4 spots, I guess, and come back when you are finished. So please pause the video and go do that now. So if you're still watching, you have finished reading the article and you've answered your own answers. I want to see how closely they match to what I might have said so that we could have a conversation. If you're confused or you want to argue, I love physics arguments, but I need you to know where we stand together. So the first question was, how will a moving object move if no forces are acting upon it? So Newton's first law basically says that whatever an object is doing, it's going to tend to keep doing. If it's staying still, it's going to want to stay still. And if it's moving, it's going to want to keep moving. And the part that's more interesting, because you might be like, well, that's pretty obvious. We had to have a whole law about that. The part that is more interesting about that is the amount of mass that something has determines how likely it is going to be to keep doing whatever it's doing. So if you have something that's really, really light and it's moving, it's not very hard to make it not move anymore, to stop it or to change its direction. Same thing with sitting still. If you have something really, really light that's just sitting there, it doesn't take much to make it start moving. Same thing with really heavy stuff, but in the opposite direction. If you have a really heavy thing flying at you, it's going to be really hard to stop it. So the first question is, how will a moving object move if no forces are acting upon it? It's just going to keep doing that same thing forever. So if you have something moving, it should just keep going forever and ever. Question number 2. If you push a shopping cart, it moves. And when you stop pushing it, it rolls a little ways and then comes to a rest. So the question that I have is, does this violate Newton's law of inertia? Because you put something into motion and then it came to a rest, it didn't keep doing what it was doing. Well, the key here is friction. If you have to push a shopping cart, if there was no such thing as friction, the shopping cart should roll forever and ever and ever until it runs into a car or something like that. But that would be a force too. So if something is moving and then comes to a stop, it means that forces must have been involved. For question number 3, why do you suddenly lurch forward in a bus that slams on its brakes? So if you are in a bus, you might look around and be like, oh, I'm at rest, I'm not moving. But relative to the rest of the world, you are moving with the bus. So you are an object in motion. So if the bus slams on its brakes, because you have mass, your mass is going to want to keep going. That's what Newton's law says. And so that's why you go flying forward. In fact, if you're a much bigger person, you're going to be an even harder object to stop. So I told you a little bit ago that people think about this kind of stuff for when they're designing cars to survive car crashes. Seatbelts have a much harder time, or they have a lot more work cut out for them if the person in a car crash is a really big person, because that seatbelt has a lot more mass to stop than if it was a little person. So you fly forward because you have mass, and you were an object in motion, even though you were just sitting still in the bus. Then the last question. So thinking about Newton's first law, objects doing whatever they were doing before, how do you give yourself an advantage in hand judo? Well, I was able to launch my own children, and probably I could do the same for you too, because I'm a much bigger person than most 8th graders. I have a lot more mass. So if you and I are pushing against each other, you have to turn an object in rest that's much bigger than you into an object in motion, and that requires a bigger force for me than it would require for you. So the best strategy that you can have if you're a small person is wait. You might have noticed in the videos when I was playing against my daughter that I would let her push against me and I would kind of pull my hands back. Well, if your opponent turns themselves into an object in motion, they're going to have a hard time stopping too because they have inertia. And so if I just get kind of lean back a little bit and get out of their way, they're going to have a hard time turning themselves into an object at rest again because they've just done all the work themselves. So if you're a small person, wait for me to do the motion part and just let me fall over. That would be your best strategy. Okay, so now in your notebook, on the left-hand side, there are just a couple of notes that I need you to take. And I also want you to take down this picture because I'm going to be referencing it in the future, and it'll be helpful for you to review back, and you can use all of this on the assessment to help you write up a good assessment. So let's break down Newton's first law. We're going to kind of do this in steps. The first thing that Newton said was that anything with mass has inertia. So if you are a tiny little grain of sand or a whole planet, and even the air you're breathing, we're breathing nitrogen right now, mostly, and a little bit of oxygen. And you learned back in chemistry that nitrogen and oxygen, they have mass. It's on the periodic table. You see the mass number at the bottom. Anything with mass has inertia. Some things have more than others, and that's the next part. And we'll come to that in the third part. The next part is inertia is a resistance to change. So in other words, anything with mass has a resistance to change. So the air that's around you has a little bit of mass, and so that's why it's not very hard to push the air out of the way. But the table I'm sitting at has much more mass, and that's why it's a little bit harder to push the table out of the way. The more mass you have, the more inertia you have. So inertia at rest is going to mean that it's going to tend to stay at rest. And inertia in motion is going to tend to stay in motion. And there's a little bit more that Newton added to that. Motion in a straight line, too. We'll talk about that more in just a minute. And the only thing that you can do to change inertia is by acting on it with a force. So in the little picture that I have, if you had two buckets of sand, or one bucket with sand and the other one was empty, the one with sand in it is going to be harder to get moving. They're both objects at rest. They both have mass. They both require some force, but the one with more mass requires more force. That's Newton's first law. If you need to pause this video to record on your note side, do that now. Okay, so we kind of already answered this from a minute ago, but that's okay. On your note side still, I need you to quickly jot down the answer to this question as you understand it so far. So why do I have an advantage with my inertia? And what's the best strategy to beat me while you're thinking about inertia? So pause the video again and jot down at least a sentence for what my advantage in hand judo is. Ready, go. Okay, one last thing on your note side. To kind of summarize what we just went through, I think that this helps a lot of people. It's kind of like a vocabulary part. So like if mass and inertia are the same thing, and they are, anything with mass has inertia. In physics, if you say the word mass or if you say the word inertia to a physicist, they mean the same thing, since anything with mass has inertia. So what's the difference between the words? Like, when would we use them? Well, on the left-hand side in green, we use the word mass to describe an amount of stuff. So you would say, like, this pencil has 20 grams of mass. But you could also say that it has inertia too, because since it has mass. But if you're using the word inertia over on the blue side, we use that word to describe its behavior. So since it has mass, it behaves a certain way, it resists. And so if ever you're talking about its behavior of resistance, that's when you would use the word inertia. So let's go back to the buckets and I'll give you some examples. So over on the left-hand side, the empty bucket, the bucket on the left has a lower mass of about 500 grams. That's how we'd use the word mass. Therefore, it has less inertia and is easier to get moving. So we're talking about the same thing. By saying it has 500 grams, we're talking about mass. By saying that it is easier to get moving, we're saying that it has a low inertia. But both of those words mean the same thing when you're talking to a physicist. Low mass means low inertia. Over on the right-hand side, the bucket on the right has a great mass of 2,000 grams, therefore it's harder to get moving. Mass to talk about an amount, inertia to talk about its behavior. So in this video that you're about to watch, there is a sphere filled with water. You're going to have a follow-up question after watching this video. All you have to do for this first part is just watch and pay attention to what the presenter says.
So how do we get everything up into space? Well, we often hear about a guy named Sir Isaac Newton, and we're going to talk about one of his first laws of motion. He has three, and we mentioned them all in various different parts, but his first law of motion is pretty important. Now, it states that objects at rest will stay at rest, and objects in motion will stay in motion. So what exactly does that mean? Well, I'm going to do a quick little experiment here. We have something called a hero engine, which is full of a little bit of water, and the only way out are through these two bent pipes that are sticking out on either side. I'm going to hang this up like so. Now this is now an object at rest. It's just sitting here, it's not doing anything. Now I'm going to fire up my trusty blowtorch, which I always get to use pretty much every day, and I'm going to try to heat the water up that's inside that sphere. Now what happens when you heat water up? Most people would tell you, of course, it's going to boil. And when water boils, it produces steam. Now in this particular case, the steam only has one way to get out, and it's the pipe on either side of our sphere. And we're also going to start to get some motion, which is that our little metal ball here is going to start to spin. And this is exactly what Isaac Newton was talking about. We had an object at rest, it just sat there, it didn't do anything, until an outside force, which in this case is the steam, starts it to spin. Now, according to Newton, this thing would continue to spin pretty much forever until it was acted upon by other outside forces. Now, I'll tell you, it's not going to spin forever, and that's because there are forces acting upon it right now. And very simply, we've got friction in the chain, which is rubbing against each other. We have gravity pulling down on it the whole time, and it has to work its way through the oxygen that's around. And eventually, it will come to a stop. Now, the really neat thing is, though, if we were out in space right now, and I started that to move out in space, we wouldn't have to worry about gravity, friction, or air resistance. This thing would continue to spin forever until possibly it got bumped into by an astronaut, a planet, or some sort of spaceship. So Newton's laws, not only do they work here on Earth, they also prove very well to work out in space. For For the H.R. McMillan Space Center and for the Express, I'm Cam Cronin.
Okay, so on your practice side this time, over on the other side of your notebook, I want you to be thinking about that machine that you just saw a video for, and I want you to answer these couples of questions. Would the machine move differently if it was twice as heavy? And if so, how? If no, why not? I need you to use the words mass and inertia in your answer. Remember the difference between mass and inertia, and if you need to go back and review, that's totally fine. But this is excellent practice for the types of questions you need to be able to answer to show me you understand Newton's first law. All right, if you are still watching, that means that you have answered these questions. So the way I would have answered this, I would love to have had this conversation with you in person, but here we are online. So if the machine was twice as heavy, it would be an object that had greater mass and therefore greater inertia. It would be more resistant to change. So if you heated up the water inside and the steam started coming out, it would still move, but it would take longer to get moving. It would require more force. More steam would have to come out in order to get it spinning. But once it was spinning, it would also spin longer. Once it was an object in motion, since it has more mass, and now that it's moving, it still has more, same amount of resistance to change, the same amount of inertia. So it's going to spin longer, and it's going to take longer to slow down and come to a stop because it has more inertia. So it's time to get a little bit more practice. With, let's say, about 3 or 4 lines of space, I need you to set up this table. So you're going to need 3 rows on your table, 3 or 4 lines on your notebook per row. So you're going to need several rows on your paper. And I need you to pause the video and set up the table to look just like what you see on your screen. Please do that now. So what I'm going to do is I'm going to show you 3 different examples of objects moving. Kind of like the video you just watched, I want you to get more practice seeing objects moving and being able to use the words mass and inertia and Newton's first law. So as you watch each video, I want you to be thinking about what is going to happen to that object based on Newton's first law. So I'm going to show you something going on in the first part, and then I'm going to explain how I'm going to change it. I'm going to modify something about the experiment, and you're going to need to predict in the second box. What do you think that's going to do to the experiment once I make that change? Then I'm going to show you, and your job is in the third box to explain with the words mass and inertia what actually happened. So if you were right, great. Explain why that happened using mass and inertia. If you weren't, no big deal. Predictions are wrong all the time. But still, explain why that happened using the words mass and inertia. Let's do that now. So now that you've had some practice looking at examples, I want to remind you what the goal of today's lesson is. Your job is to be able to restate Newton's first law of motion. That's a pretty low-level part. The part that's most important is extend it to everyday circumstances. So you need to be able to develop the skill of looking around in the world and seeing objects and how they move, and being able to see Newton's first law happening in everyday circumstances. So in order to continue practicing that, here's what your closure is all about. So there's this video from a channel called Smarter Every Day. This one's kind of old at this point. But he's going to be driving in his car with a balloon in the middle of his car, and there's a really excellent example of Newton's first law. Over on your practice side, after you're finished watching the video, I need you to use your words mass and inertia to explain why the balloon does what it does. So you'll see what happens. And he actually even explains it in the video. And if you need to steal his words, by all means, steal his words.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So today we're in the rocket van, and I've got two little science helpers here, right?
Yes.
Are you wearing your seatbelts?
Yes, sir.
Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go? What do you think? 3, 2, 1, go.
Yes.
Which way is it going?
My way.
That's right. It's because I'm accelerating, right? Does that make sense to you guys?
Yes, sir.
Okay,
Yes, sir.
very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. And we should see the same thing, right? Let me cut this off. So what we're going to do is we're going to accelerate that way. So we have the mass of the balloon and the acceleration, so that should net in a force, and we'll have to react with this string, right? You guys ready?
Yes, sir.
3, 2, 1.
So before he actually does it, I want you to be thinking about what should happen. Make a prediction in your mind. What should happen to the balloon? Well, if you've already read the prompt, you will know that the balloon does something kind of funny.
Go.
Oh.
Wait a second. What just happened? Hold on, what happens when I stop? The balloon goes backwards when I stop. What's happening?
It's going the same.
3, 2, 1, go. There it is. It's coming right at me. Why is it doing that? Do you want to know?
Yeah.
I brought something to show you.
Before he shows you the answer to this, I want to give you a chance to see if you can think of the answer on your own. Pause the video. Why did the balloon go forward when the car accelerated? When the metal pendulum did what you expected it to do, and the metal pendulum went backwards. What's different about the balloon and the situation in this video to make that happen? Restart the video once you think you're ready to go.
You remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar, and all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top, because the helium in the balloon is lighter than air, right? So that causes it to do what?
Go up.
Go up, that's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can get this. Okay, so I've got my seatbelt on. If I drive forward real fast right now, which direction is the balloon gonna go?
Forward.
Why will it go forward?
Because all the air is splashing back.
That's right. Very good. Watch this. Whoosh. Look at that. You see that? So you know what that means, don't you?
Yeah.
That means you have more air to breathe than Daddy does when I'm going fast. Did you realize that?
No.
Yeah, that means when I go fast, that means more air sloshes back there to you, and you have more oxygen to breathe. Doesn't it feel good back there? Okay, so now we have the plumb bob right next to the balloon. So if I go forward, they should spread apart, right? Let's check it out. Is it working?
Yeah.
So as you think about answering this question, use the words mass and inertia to explain why the balloon goes forward when the van speeds up. If you're struggling at all, I want you to think about how there are 2 objects in this video, 2 objects that we care about. The object that you're probably focusing on is the balloon, which is filled with helium. And if you remember, helium on the periodic table is a very small and light element. It has low mass. But there's also the air in the van. A lot of times people forget that air, even though it's really light, air has mass too. And since it has mass, it has inertia. Hopefully that helps you to answer your question. To close out today's lesson, make sure that you have the work that you did from the reading that you worked on with Cami, the 4 questions, and the highlighting. And you also need to take a picture of your practice page and attach it to the assignment. The thing that I'm most interested in reading from your practice page is your closure, where you're talking about the balloon, and the 3 practice stations that you saw from videos in my classroom. Once you have those things attached in Google Classroom, you are finished with today's lesson.